Okay, it's right on time. Yeah, let's get started. Please get seated. Yeah, good morning. It's day 2. Just a quick housekeeping announcement. Today is fairly straightforward. We will have morning session, technical talks, and then after lunch, we'll have a lab tour. We have 2 major lab buildings, one in building 5, which is our office building, and the other one opposite side of the campus. So we will divide the group into 2, and we will do 1 hour each, and then swap the group to the other side, and that's a plan. So that'll go starting from 2 p.m. all the way to the end of until 5 p.m. with including some coffee break in between. After that, starting at 5, we'll go to the library building. There will be a poster session where all the fellowship students will present their poster, and some of our COW students will also show some of that. So this will end with some refreshments will be served, and that'll end the schedule today. So this morning, and let me also remind you one more time, those who are the special guests, the speakers, we have arranged fantastic Al-Balad Old Town Jeddah trip tomorrow. You must have invitation in your mailbox. Please make sure to sign up within today, so we know the exact head count. Okay, so with that, let's get started. Today's morning session will be chaired by Gaetano Magnotti.
Thank you.
Thank you.
Good morning, everyone. I'm Gaetano Magnotti from KAUST. So this morning, the first session this morning is land mobility. This is the second session on this topic. The first speaker today is Michael Brear is the director of the Melbourne Energy Institute at the University of Melbourne. He guides the Institute research on the technical, economic, environmental, and social impacts of energy systems. His own research is collaborative with industry and government on the technical, economic, environmental analysis of transport and energy systems with reciprocating engines and gas turbines, and conventional alternative fuels. Michael, please go ahead.
Thank you, everybody, and I'll just share my screen. Can you hear me clearly? Yes? All good to go?
Yes.
Terrific. Well, look, thank you, everybody, and I'll talk to you today about autoignition, knock, detonation, and the octane rating of hydrogen. Some very fundamental and perhaps basic concepts, but as I'll show today, I think some interesting things happening when we look at this closely. Before I get into the details, I would first like to thank KAUST for the invitation to speak today, and in particular Professors Roberts, Im and Turner for inviting me. My sincere apologies for not being able to be with you today. I have various things going on at home with aging parents and things like that, which mean I can't travel overseas at the moment. So I'm sorry I'm not there, but thank you very much for inviting me. I look forward to seeing you all in person shortly. I also acknowledge my colleagues at the University of Melbourne, particularly Dr. Farzad Poursadek, who undertook the experiments and modelling that I present today, and it's actually just been published. So this paper just appeared a couple of weeks ago in Fuel, and is really what we're talking about today. I encourage you to have a close look at it. So this is really the core of the discussion today, and that supposedly simple question, which you would think might have a simple answer, has led us to write this paper. So we'll go through that in some detail, but you might know the answer already, you might not. Other people have said what the answer is, and there's a large range, as I'll discuss. So the literature on hydrogen susceptibility to knock is contradictory, and it's not particularly traceable. So there are studies out there that say hydrogen's high octane, others say it's low octane. We found studies that say the RON of hydrogen is as low as 60 or over 130. So that's quite a range. And also importantly, we were unable to find primary references that report these octane ratings. So quite a few studies report RONs for hydrogen, but they were, when we dig and dig, we find that those studies refer to other studies, and we weren't able to find a primary study that looked at this in any detail. I'm not saying for a minute that they don't exist, we just weren't able to find them. Now, of course, hydrogen, as you well know, has a high autoignition temperature and a high flame speed, and that suggests that it will have superior knock resistance. But we also know that hydrogen has low ignition energy, and that could potentially initiate uncontrolled combustion and might therefore complicate matters in an octane rating engine, for example. And then finally, the apparent absence of unpublished studies that demonstrate how the RON and MON of hydrogen were measured calls into question these reported values. Similarly, the reliance of the methane number, which is used for rating natural gases, on the assumption that hydrogen is knock prone, is inconsistent with studies that suggest that hydrogen has high octane. Methane, as you know, is often rated above 120, similar to the higher range of those in the literature of hydrogen. So a study that clarifies this situation using a standard octane rating engine, we think is a useful thing, and we hope that you agree and read our paper accordingly. Now, in terms of experimental methods, we're doing all this work, as I mentioned, in the standard octane rating engine, the Walker-Shaw CFR F1, F2 engine with variable compression ratio. Now, of course, that engine's designed for rating liquid fuels, so that when you modify it to study gaseous fuels, you have to change the fueling system so that you can do so. And the way we've done that is by equipping this engine with a gaseous fueling system, but retains the standard carburetor in the CFR engine. Now, straight away, by action of doing that, we're making the engine non-standard. So we need to be careful about when we depart from standard test procedures with a standard engine, that we, if we can possibly, maintain the intent and the key physics of the use of the standard engine. Now, we think we've done that, and I can talk about that a little bit later on. Now, two sets of octane rating tests were conducted. The standard tests based on ASTM's RON test method. And we also did modified tests where hydrogen was rated at lambda values that were more relevant to SI engine operation and with spark timings that matched the combustion phasing of isooctane at its standard test condition. You'll see why we've done that when I show you some of the results later on. Then, of course, pretty standard instrumentation. We just use a Kistler 6125 piezoelectric pressure transducer for measuring in-cylinder pressure. And importantly, we did not see pre-ignition in this engine at any of these operating conditions. And that's, as you know, important for studies of hydrogen. But on the right-hand side there, you see typical conditions for the RON standard test: engine speed of 600 RPM, intake air temperature of 52 degrees Celsius, coolant temperature that's boiling, and variable compression ratio depending on the standard knock intensity or your tuning with different fuels. Now, in terms of numerical methods, also pretty conventional approaches. Two-zone combustion modeling using GT Suite. That allows us to take the in-cylinder pressure trace. We use what we call the representative pressure trace, which is that of the 1,000 measured or so, which has its IMEP closest to the average of the 1,000. When we use that, we can then back out the mass fraction burnt and the in-cylinder heat transfer from that two-zone combustion model. But of course, in order to do that, we need other things. We need the volumetric efficiency, residual gas fraction, and wall temperatures. And that requires us first to do a full engine model that we have done and which we have reported previously. We also will do later on, I'll present some results of turbulent flame speeds. So we're going to be using GT Suite's turbulent flame module for presenting some of those results. Although that's not essential for our studies of autoignition. Now, in terms of autoignition, we just do a very simple closed homogeneous adiabatic reactor in Kenken. We impose on that adiabatic reactor the charge temperature and composition at intake valve closure that we've obtained from our GT suite models, and the measured non-auto-igniting pressure traces are imposed on this reactor. Now, you'll see later on how we obtain, at a given experimental condition, the non-auto-igniting pressure traces. And that's a bit of a trick that we've developed and presented about 5 or 6 years ago at a combustion symposium, the one in San Francisco. Now, autoignition was modeled using, well acknowledged kinetic model with a nitric oxide sub mechanism. That's the model of Zhang et al. From Combustion and Flame in 2017. So all pretty conventional stuff. Now, this is where we start to see some results and some strange things with hydrogen. So here we are plotting the knock intensity from the knock meter, which is part of the ASTM test procedure. Think of this roughly as the peak rate of change of the in-cylinder pressure with respect to theta, crank angle. And you can see here straight away we're doing hydrogen has a peak knock intensity at very rich conditions, roughly lambda 0.7, a little bit less. And you can see, in order to develop any octane number, what you do is, of course, get 2 PRFs that bracket that fuel, and one which has a slightly higher knock intensity and one which has a slightly lower knock intensity. So straight away, you're seeing some strange things with the standard RON test. That is, the PRFs, 62 and 66 in this case, bracket the hydrogen in terms of knock intensity, but they do so at a much richer condition. And sort of 0.85 to 0.95 lambda is what you find hydrocarbon fuels in general. Gasolines, typical gasolines, will be reaching their peak knock intensity at those sorts of conditions, and you commonly see the PRFs doing that. So straight away, we've got a bit of a clue that something is going on with hydrogen that's weird. Now, if you look at the in-cylinder pressure trace, I apologize, you'll see this in a moment. Here is top dead center. I might even be able to do, I won't get too clever, sorry, excuse me. If you can see my mouse, that's top dead center there. So here's isooctane at its standard knock condition. You're seeing, of course, that's this open circle is the CA50, and its CA50 is happening at about 9 or 10 degrees after top dead center, as you would expect. So there's 0, 10, 20, 30. There's minus 13 degrees, which is the spark timing in the RON standard test. So minus 13 degrees, ignition, deflagration, off you go. Then there's auto ignition kicking in here roughly. We'll talk about that later on, but you see, as you would expect, CA50 between 5 and 10 degrees after top dead center, as is conventional for SI engines. But when you're running hydrogen at this peak knock intensity case, you're seeing that the spark is starting at the same time, minus 13 degrees before top dead center, but peak pressure is happening before top dead center, and so is CA50. So that's not very physical of a production, representative of a production engine. If we look at the rates of change of pressure, so the first and second derivatives, you see, interestingly, the clear spikes that you see typically of auto ignition occurring in for isooctane, and you're seeing here peaks in the first derivative that are of comparable magnitude to those here, where we're confident that we know that auto ignition is happening. So this stuff here is measured with the 6125 Kistler, not with the knock meter and everything else from the ASTM standard. So we are seeing peak rates of pressure rise that are comparable to knock at isooctane or standard RON measurements. Now, but the spark timing is a concern, and clearly having peak pressures in CA50s before TDC are not very practical. So what spark timing should we use for modified RON tests if we want to understand this behavior? Because at the standard test condition, where we would argue that we're at very unrepresentative test conditions that don't really mean a lot for real engines. So, oh, well, here's the CA50 that you get if you go from a very low RON fuel up to a very high RON fuel. And you can see, unsurprisingly, you know, for conventional spark ignition fuels, the CA50 is mostly between 5 and 10 degrees. So we will then suggest that the modified RON test should have spark retarded for hydrogen such that its CA50 is close to that of PRF 100 at standard condition. So about, you know, 9 degrees after top dead center. So if we then retard spark, and in this case, we're sweeping lambda. So clearly running an engine at lambda 0.7 is pretty silly. So we're going to run the engine at stoich and through to lean. We won't go leaner than lambda 2. We could, and you'll see later on why we don't for this study. So here we are, lambda 2 for hydrogen, lambda 1 for hydrogen. This is 0. This is top dead center here. And you can see the spark timing goes from after top dead center to about top dead center to in front of top dead center, so before top dead center, as we increase lambda. Associated with that are the rates of pressure rise, and you can see this, we're seeing clear spikes at around about 10 degrees after top dead center, where we'd expect it to be, and we're starting to see therefore something which is more in keeping with what we would see for a standard hydrocarbon fuel. Now, that's not the full picture, because we also have to think about why are we choosing what lambda. So the ASTM method tells you for a standard gasoline that you should rate it at its standard SKI condition, which is the lambda value and compression ratio at a given compression ratio that gives you peak knock intensity. And if you therefore say, well, hang on, we can't do that because we know that it's going to be extremely rich. So then how do we choose a lambda value that is more representative of what we would see in practice? Well, one guide would be to say, what value of lambda should we run hydrogen engines at such that it delivers, the chemical energy delivered is equivalent to a more conventional SI engine fuel. So for example, for gasoline, if we run a stoichiometric gasoline engine, we should get the same amount of energy going into it from hydrogen if we run at lambda 1.24. And you see for most of these fuels and these hydrocarbons and alcohols that we're running about between lambda 1.2 and lambda 1.3. If you had a lean burn engine for, of course, like a big natural gas engine, or even if you ran trying to achieve comparable power to a diesel engine, you would run it leaner conditions. So you need to run between lambda 1 and 2, we think, to match the power output of most conventional fuels. And as we all well know, these are typical values here for the octane number and the critical compression ratio, the compression ratios that these different fuels run at. Now, okay, so we're going to choose, let lambda float to be somewhere between lambda 1 and lambda 2, as I've showed previously. And if we do that, because we're not going to take a fixed view on which lambda it should be, this is the modified RON that you get. So for these 3 different lambda values, we vary the spark timing so that the CA50 matches that of isooctane, and we then infer the octane number from that. So we see for lambda 1, with the spark timing of 3 degrees after top dead center, we get about a 94 octane number for hydrogen. If we run at lambda 1.5, we get 117. And if we run at lambda 2, we're above 120. And the ASTM method formally doesn't go above 120. And it's also very hard to rate at those conditions. So we just say it's high, above 120. So we're getting those high octane numbers when we modify the test carefully such that we consider these conditions to be more representative of practical engines. Now, if we look further, we can start to examine now what we are expecting to see in terms of is this engine knocking, at what conditions, and how. So this is the kind of thing you see if you plot the raw pressure trace. The black line is for isooctane at its SKI condition standard RON condition. And you can see a little bit of the wiggles there due to the acoustics in the chamber post auto ignition. Then the red line there is what you get if we dose the isooctane fuel with a very small amount of TEL. Typically this is dilute TEL. It's the standard stuff you use for rating octane engines. You put in of order 0.5% or 1% also into the isooctane. So what you see is that red line suppresses this auto ignition event, but if you use sufficiently low amounts of it, you don't change the compression and deflagration. Remember that this is top dead center here, and spark ignition's happening around about here. So sorry, have I got that right? I think I have. I'll just check in a moment. So small amounts of TEL allow you to suppress NOC, and we would argue at the same time have negligible effect on the turbulent flame propagation prior to auto ignition. So if we do the same thing at these modified RON conditions, we get interesting things happening. So I'll first focus on the lambda 1.5 case. So that one's a little bit less energy per unit volume introduced to the engine than it would be for a typical gasoline. But you can see with this small amount of TEL added once again, no effect on the compression, no effect from spark through the deflagration, and then this noticeable suppression of auto ignition in the trace without TEL added. And similarly, you're seeing it at lambda 2. Not much happening on compression and spark from spark ignition through deflagration, and then a progressively larger departure once auto ignition is occurring. But interestingly, at the lambda 1 case, you're seeing very little impact of TEL on what's happening in the cylinder. Remember, of course, that these three cases here are all at different compression ratios. Hence, you can see the motoring traces, or the pre-combustion traces have very different trajectories. But TEL has no effect in this case at lambda 1, at this modified condition for lambda 1, but it has a noticeable effect at lambda 1.5 and 2, just as it does for isooctane. And we've seen very similar behaviours when we've looked at C3s and C4s and other PRFs. So conventional behaviour here, unconventional behaviour there. What else is happening at stoichiometrically? So the plot is thickening. We're seeing some strange stuff at lambda 1. Here, we just went back to lambda 1 and we had a little bit of a look-see. And you can see here some raw pressure traces. Here's the blue trace, which is what happens in that lambda 1 condition. I can't remember, it's +3 degrees spark timing after top dead center, low compression ratio, 6:1. And all we're doing here is, for this stoichiometrically fueled engine, is increasing its compression ratio. 6:1, 7:1, 8.5:1, 10:1. And you can see these wiggles starting to appear, starting to become noticeable. What's interesting though is, from memory, about 0.5% of all cycles at 8.5:1 are starting to exhibit this kind of behavior, with peak pressures up around 120 bar. When we go up to 10:1, it's about 1 in 3 cycles from memory, going up to above 150 bar. And if you look at those peak pressures and do a little bit of conventional Chapman-Jouguet analysis, you find out pretty quickly that that's detonations occurring. So a naturally aspirated hydrogen-fueled CFR engine running at stoichiometric conditions, you can detonate it if you run at too high a compression ratio. And you don't see sort of conventional auto ignition and knock occurring before that happens. So let's, for a moment, just park that, and we'll look a little bit more at the combustion modelling. So here we've got pretty standard GT power kind of results. Here's the trace, the standard stuff that we get our graduate students to do. There's the mass fraction burn that we get from a GT power trace for isooctane. And then we see here, when we run hydrogen from lambda 2, 1.5 and 1, that is from the leaner conditions to the richer condition, and therefore from the slower burns to the faster burns. At lambda 2 for hydrogen, you're getting MFB profiles that are pretty similar to those of isooctane, but then when you're running stoich, you're getting a much faster burn. Then if you go and when you look at this modeling in further detail, we've used correlations from Verhelst for the laminar flame speed. They seem to be as good as any when you're at these kinds of representative temperatures and pressures. You're seeing very high laminar flame speeds in cylinder at these stoichiometric conditions, as you might expect. And as you're going leaner, you're going back towards what you would expect for isooctane of order 1 to 2 meters per second. Now, in terms of turbulent flame speeds, you're seeing then equivalently very rapid burns for the rich condition, for the stoichiometric condition on hydrogen. And as you're going from lambda 1 to lambda 1.5 to 2, you're getting back to turbulent flame speeds in the CFR engine that are approximating those of isooctane and typical hydrocarbon fuels. And then, of course, the gas expansion, taking into account gas expansion, you're seeing very high velocities in the chamber, where that's the superposition, of course, of the expansion of the flame due to density stratification, as well as the turbulent propagation. And once again, this very, very distinct change, where at lambda 2, the engine is looking more like a conventional hydrocarbon engine, but stoichiometrically, it's certainly not. So we can get that's starting to tell us something about the burns and what might be happening. If we then go into the one zone kinetic modeling, we'll see these kinds of results. So remember that we've taken the temperature at inlet valve closure from the GT power model. We've taken the mixture. We've assumed it's homogeneous from the GT power model. So we've got the hydrogen and the air from a given lambda. We've got the residuals from the GT power model. We've homogenized that into this Chemkin homogeneous reactor. And then we're compressing it from that adiabatic condition as per the imposed in-cylinder pressure trace. Now you see, as that happens, here's the temperature. For example, let's start with lambda 2. Here's the temperature here going along. All of a sudden, bang, the temperature goes up, and you recognize that, of course, as autoignition. Here's the normalized hydroxyl radical concentration, and of course, it's coincident with the temperature rise. So that point there is the autoignition point in the engine. This point here is the measured autoignition point from the experiments for that operating condition, and this is the mass fraction burn profile we've obtained from the GT power models of the measured pressure trace. So at lambda 1.5, we did the same thing, and we see the temperature going along, and then up she goes. And then we see once again now within a few crank angular degrees of the measured autoignition point, closer agreement. But interestingly, at lambda 1, we see autoignition happening basically at the end of the burn, and we didn't see in the engine an equivalent point to these measured autoignition points. That's that noticeable rate of a great change in gradient of the pressure trace from inside the engine. So if you then start, we've assumed these models here with different temperatures at inlet valve closure and different residual NOx concentrations. These are the measured NO emissions in the tailpipe, and then we dilute that, with the fresh charge to get a representative mixture in the intake. But of course, the NO concentration temperature at IVC is of course non-uniform, reasonably uncertain. So it's sensible for us to vary those over some ranges and see how sensitive these simulations are to those two particularly uncertain parameters. If we do that, we see that we get, for changing the NOx concentration by half to double each of these numbers, you get a pretty small change in the autoignition timing for each of these cases. But if you change the IVC temperature from plus or minus 15, 20 degrees Kelvin from memory, you get a larger change. And you can see here, for example, for the lambda 2 case, if you vary the TIVC, you can easily get the autoignition timing in simulation to exceed anything seen experimentally. Similarly at lambda 1, but importantly, we never see autoignition with sweeping nitric oxide or TIVC during the burn at that lambda 1 condition. So summary and conclusions. Application of the standard RON method showed that hydrogen had a RON of 62 to 64, but this standard method required very rich operation on hydrogen at its standard knock intensity, CFPRFs of similar RON. The resulting hydrogen combustion featured 50% mass fraction burn occurring before top dead center, indeed peak pressure before top dead center, so not very useful. So modified RON tests were therefore undertaken from lambda 1 to 2, with the spark timing retarded such that the location of hydrogen's MFB 50 matched that of isooctane at the standard condition, and all other parameters were maintained as per the standard RON method. This modified RON testing is more representative of practical engines and indicated that hydrogen at lambda 1, 1.5 and 2 had a modified RON of about 94, 117 and above 120 respectively, with these lambda values spanning those that match the energy delivered by common SI engine fuels. But these modified RON tests also demonstrated different abnormal combustion regimes between lambda 1 and 2. Between lambda 1.5 and 2, at these SKI conditions, we saw pressure traces featuring deflagration and then autoignition followed by a rapid pressure rise, and that's pretty commonly seen when we're doing work in these engines. The addition of small amounts of dilute TEL suppressed that rapid pressure rise without modifying the earlier burn. At lambda 1, however, and these SKI conditions, the rapid pressure rise wasn't observed, and the addition of TEL had negligible effect, and these suggest no autoignition is happening at those cases. Indeed, detonation started to occur as the compression ratio was increased above that at standard knock intensity after first appearing at around 8.5 to 1 compression ratio. The numerical modelling demonstrated consistent trends to the experiment. At lambda equals 1, we saw turbulent flame speeds of order 15 to 20 meters a second and autoignition timings that were very near the end of combustion. Whereas at lambda 1.5 and 2, we saw turbulent flame speeds more typical of conventional fuels, and these enabled autoignition timings close to those seen in the experiments. So together, we can say that hydrogen can be more knock resistant than standard gasolines when used appropriately. Maybe watch out if you don't, though. You don't want detonations happening, and it requires careful application and interpretation of standard test methods. I would argue that the blind use of the RON method to rate hydrogen is misleading and indeed pretty meaningless, and it requires the careful use of diagnostic tools to avoid mistakenly classifying normal and abnormal combustion. It looks like a lot of these very fast burns are actually just conventional fast burns and not autoignition, and they're very hard from rates of pressure rise to separate between the two. So thank you.
Thank you, Michael. Any question, please come to the microphone. Somebody's coming.
Thank you for the very nice talk. I just wonder if you considered modifying the operating conditions of the CFR for the MON conditions, so motor octane number, so you can quantify the octane sensitivity and the knock index. Thank you.
We haven't yet. It's a very good question. We might do it, but haven't yet.
I have first a question. So in your study, you try to monitor the RON number under different equivalent ratio, the lambda, and you keep changing the pressure, so you can see the lock tendency very different, like the K of lean condition more prone to autoignition. However, if you run in practical condition, like you keep the same high boost condition, and if you want to match the combustion timing, you vary the spark timing too much, the combustion phasings. Maybe the knock tendency for the rig case very prone to detonations.
Yes, so you're talking about what happens when you add boost into the problem?
Yeah, because in the experiment, you just try to fix the combustion phasings by advancing spark timings for the lean condition, right? However, if you keep at the same boost condition with lean and the stoichiometric mixture, but you try to delaying the spark timing for the stoichiometric mixture, so maybe it still can produce very high lock intensity for the stoichiometric condition, right?
Yeah, I think you're asking if you for example maintain power by varying lambda with boost level, what happens? Is that what you're asking? I think then lambda is then a function of boost level. Obviously, for this RON standard engine, it's a naturally aspirated engine, and we've actually designed a boosting system now where we're looking at trade-offs between boost and lambda and auto ignition. So I think we're on the same page, and I think there's a lot that can be done when you're looking at that parameter space.
Okay, thank you.
Thank you.
Thank you very much. I'm just curious to know more about this modified RON test and that lambda sweep that you've done. So with gasoline, does it behave the same? So we saw a 94 at lambda 1, then a 117, a big jump to above 120. Is it like this, for example, with a RON 95 gasoline? Would it follow the same trend as you go lean?
Good question. We've never done that test because you run gasoline engines close to stoic in practice, so not necessarily, but you would of course expect the effective octane number to go up as lambda increases. But with hydrogen in particular, you can run at very lean conditions and still get complete combustion. So if on this engine you start to get terrible combustion on gasolines at around about lambda 1.2, 1.3. But the conventional RON standard forces you to run at around about lambda 0.88, 0.89 on gasolines as part of the standard test procedure. I think you're right. We haven't done that test.
Okay. I mean, the reason why I'm asking, I mean, in real, we do these RON tests to know how would a fuel behave in a real engine. So
Correct.
What's your take? Is hydrogen like a 95 RON gasoline? Is it, from what I'm taking, at least?
Well,
okay, it's the flame speed is so fast for you to take the standardized spark timing. I agree with maybe a shift in the spark timing, but it seems like it's very similar to a 94 PRF.
Well, I think it's sorry, let me just bring up the modified RON from lambda 1 to lambda 2 is a modified RON of 94 to 117 to a higher number. If you, for example, wanted to match the energy input of a stoichiometric gasoline engine, you'll run a hydrogen engine at about a lambda 1.25, and then your octane number will be roughly halfway between those two variable numbers. Okay. Of order 105, similar to ethanol, I'd say 105, 110.
Thank you very much. Thank you.
Okay, let's thank you, Michael, once again.
Thank you, and have a good day.
Thank you.